The moon has a secret side, not a metaphor, not a figure of speech, a literal physical hemisphere that has faced away from every human eye for the entire history of our species. A side that never turns toward us. A side that, until very recently, no living person had ever seen directly with their own eyes from space. On April 6th, 2026, 4 astronauts changed that. They swung behind the moon in a spacecraft named Integrity, cut off from every other human being alive, floating in a silence so complete it has no analogue in any human experience. And what they described when they came back around did not match any photograph, any satellite image, any dataset that NASA had ever collected. The colours were wrong, the terrain looked alien. And one of them, a man who has flown to space before, he was trained for years, he has studied the lunar surface in more detail than almost anyone alive, looked out the window and said something that stopped mission control cold. Humans probably have not evolved to see what we are seeing tonight. Before the flyby was over, the crew had witnessed 6 explosions on the lunar surface, bright enough to see from thousands of miles away. They had broken a distance record held for 53 years in total silence, with no one to celebrate with. A man had named a crater after his dead wife, and 4 astronauts had wept together in the dark, floating in microgravity, 252,756 miles from home. And then came the eclipse. 57 minutes of totality. Nearly an hour of the sun vanishing behind, a black orb, while the solar corona wrapped around it like a crown of white fire. The longest eclipse any human being has ever witnessed. Viewed not from the ground, not from an airplane, but from 4,000 miles above the surface of the moon itself. This is what Artemis II actually saw. And it begins, as so many of the most important things in the history of exploration begin, with a flash of light. The date is April 6th, 2026. The time is 8:35 in the evening, Eastern Time. Commander Reed Wiseman is floating at a cabin window of the Orion spacecraft. The moon hangs in front of him, dark. The sun has just slipped behind it from his perspective, and the entire lunar disk has gone black, a perfect circle of nothingness rimmed by the ghostly white glow of the solar corona. He is 4,000 miles above the lunar surface. He is 252,756 miles from Earth. That is farther from home than any human being in the 300,000-year history of our species has ever travelled. Farther than Apollo 13, farther than Apollo 8, farther than every expedition, every voyage, every journey that any member of our species has ever made in either direction. And the moon below him is exploding. Not dramatically, not all at once. In pinpoints, brief, sharp, fierce little detonations that last less than a second and then vanish. A flash, a pause, another flash. Rocks from deep space striking a world with no atmosphere, no friction, no defense of any kind, at velocities exceeding 40,000 miles per hour, vaporizing themselves on contact, excavating craters, releasing energy in brief bursts of light, hot enough to melt steel. Wiseman reports the first flash to mission control, then another, then 2 more that he cannot report immediately, because by then the spacecraft is swung behind the far side of the moon. Every radio link to Earth has gone dead, and the screens at Johnson Space Center in Houston have gone dark. Canadian astronaut Jeremy Hansen sees those 2. He and the crew are the only witnesses. 4 human beings watching explosions on another world with no way to tell anyone. By the time the flyby ends, the crew has logged 6 confirmed impact flashes. 6. In 7 hours. NASA's lunar science lead Kelsey Young responds with barely contained excitement, pointing out that citizen science networks on Earth have been monitoring the near side of the moon simultaneously. Amateur astronomers with their own telescopes, organized through programs like the Unistellar Citizen Science Network, may have captured some of the same events. For the first time in history, human eyes in lunar space and telescopes on Earth might have observed the same impact events at the same moment. The scientific value of that kind of cross-verification, triangulating the exact location and energy of each impact from multiple perspectives is, Young says, extraordinary. But the flashes are not supposed to be surprising. Not to the scientists. To understand why, you have to understand what the moon actually is. Not what it looks like from your backyard, not the pale silver disk that rises over the horizon on a clear night, but what it physically is in terms of its relationship to the solar system. The moon is a target range. It has no atmosphere, no magnetic field worth mentioning, no ocean, no weather, no erosion in any conventional sense. There is nothing between its surface and the void above it. Every piece of debris that crosses the moon's path, every grain of sand, every pebble, every boulder tumbling through the inner solar system, arrives at the surface at full speed. On Earth, we are protected by an ocean of air roughly 60 miles deep. Every day, approximately 48 tons of space debris enters our atmosphere. Almost all of it burns up. The friction of atmospheric entry converts the kinetic energy of those incoming fragments into heat and light, and they vaporize harmlessly miles above our heads. The shooting stars you see on a summer night are tiny fragments of rock and ice being destroyed by that friction before they ever get close to the ground. On the moon, there is no such destruction. Every grain arrives, every pebble arrives. Every rock arrives at whatever speed it was travelling through space, which is typically somewhere between 20 and 72 kilometers per second. That is, 45,000 to 160,000 miles per hour. At those velocities, a rock the size of a golf ball carries the energy of a small explosive device. It slams into the regolith, vaporizes itself and the material around it instantly, excavates a crater far larger than itself, and releases a flash of energy hot enough to briefly approach the temperature of the solar surface. NASA's Meteoroid Environment Office at Marshall Space Flight Center in Alabama has been watching the moon for exactly these events since 2005. Using twin telescopes, they have logged more than 443 candidate impact flash events over 2 decades of monitoring. Across the Atlantic, the European Space Agency's NELIOTA program, Near-Earth Objects Lunar Impacts, and Optical Transients, operated a 1.2-metre telescope at the Crinary Observatory in Greece between 2017 and 2023 and detected 192 validated impact flashes. In August 2025, a new 3-year observing campaign began, extending the monitoring into the Artemis era. The numbers that emerge from this data are quietly staggering. The entire lunar surface is struck by approximately 7.4 sporadic meteoroids per hour under normal background conditions. During meteor showers, when Earth and Moon pass through the debris trails of comets, that number rises to 12.6 per hour. The rocks are mostly small. 75 to 80% have masses under 200 grams and radii under 3 centimeters. But they are moving at speeds that convert small masses into enormous energies, and they have been doing this for 4.5 billion years without interruption. This is why the moon looks the way it does. Every square meter of its surface is cratered. Every pebble-sized depression, every boulder-sized pit, every vast ringed basin is the record of an impact. The moon's surface is not a landscape shaped by geology in any conventional sense. It is an archive of violence, a surface that has been hammered continuously for longer than life has existed on Earth, and is still being hammered right now. The Artemis II crew saw 6 of those hammerings during a single 7-hour flyby. Victor Glover, the mission pilot, describes it in terms that a scientist would not typically use. He says it is truly hard to describe. He says it is amazing. He says it in the same breath as his comment about human evolution, that our brains were not designed by natural selection to process what they are looking at. And he is not wrong. The human visual system evolved to perceive a world defined by geological stability, by slowly changing landscapes, by the absence of random high-velocity impacts. The moon, seen from close range, is something our perceptual systems have no category for. But the flashes are not merely beautiful, and they are not merely scientifically interesting. They are operationally critical. Because NASA is not just visiting the moon. Artemis III will land astronauts on the lunar surface. Artemis IV will build a space station in lunar orbit. Future missions are designed to establish a permanent human presence, a base, a habitat, the first real foothold of sustained human activity on another world. And every single one of those missions will have to reckon with the fact that the moon is continuously under bombardment. Nelio to round the numbers. A small structure on the lunar surface, something covering less than 400 square meters, faces a probability of roughly 0.29 of being struck by a detectable meteoroid within a decade. That sounds negligible. But scale it up to a larger complex covering 8,000 square meters, and the worst-case probability of an impact within the decade climbs to about 0.9%. A space station in lunar orbit for 5 or more years carries an estimated 1 to 2% chance of impact. And those figures only account for impacts large enough to produce a detectable flash. The micrometeorites, particles too small to generate visible light, are excluded from the calculation entirely. They exist in quantities that make the larger impacts look rare by comparison. For an astronaut conducting a spacewalk on the lunar surface, a centimeter-sized rock travelling at 40 kilometers per second is a projectile moving faster than any bullet ever fired on Earth. No spacesuit currently in existence is designed to survive that kind of impact energy. There is no warning system, no atmosphere to slow the incoming fragment, no friction to generate heat and reveal it, no sound to announce its approach. The moon is beautiful in the way that a high-speed river is beautiful. You can admire it from a safe distance, but anyone who steps into it needs to understand exactly what they are dealing with. The 6 flashes that the Artemis II crew saw are a reminder of that reality. Brief, bright, gone in less than a second, and each one of them a small demonstration of what the lunar surface has been enduring for the entire history of the solar system. At 6:44 in the evening on April 6th, 2026, the Orion spacecraft slipped behind the moon. One moment, NASA's Deep Space Network, a chain of enormous antenna stations in California, Spain, and Australia, was tracking the crew with perfect clarity. Telemetry was streaming. Life support readings were nominal. The voices of 4 astronauts were coming through clear and steady. The next moment, silence. The moon's bulk blocked every radio signal, every data stream, every connection between the spacecraft and the rest of humanity. At Johnson Space Center in Houston, the screens went dark. Flight Director Judd Freeling had warned the team. He had told them that physics would take over, and that physics would absolutely bring the crew back around. But physics does not talk back. And for the next 40 minutes, no one on Earth could do anything except wait. The crew had been briefed on this. They had trained for it extensively. The blackout is a known feature of any mission that swings behind the moon. It is not a malfunction, not an emergency, simply an unavoidable consequence of the geometry. Radio waves cannot pass through 4,000 miles of solid rock. But there is a significant difference between knowing something intellectually and experiencing it in your body. And what the Artemis II crew experienced during those 40 minutes is something that no simulation, no matter how sophisticated, can fully prepare you for. They experienced complete isolation. Not the isolation of a quiet room or a remote wilderness. Not the isolation of losing cell signal on a country road. This was absolute isolation, in a way that has almost no equivalent in human experience. There was no backup channel, no emergency frequency, no satellite relay, no alternative pathway of any kind. 4 human beings, sealed inside a capsule roughly the size of a large SUV, floating in the void behind the far side of the moon, with no line of sight to any other human being anywhere on Earth or anywhere in space. They were, in the most literal possible sense, alone. And during that silence, they watched Earth disappear. It is called Earthset, a word that feels somehow both precise and insufficient. From the perspective of someone in lunar orbit, the Earth rises and sets just as the sun rises and sets from Earth's surface. As Orion swung behind the far side, the crew watched their home planet drop below the lunar horizon and vanish. One moment, it was there, a bright blue marble hanging in the black, impossibly detailed, impossibly familiar. The next moment, it was gone, swallowed by the edge of the moon, the only home every human being has ever known, hidden behind 4,000 miles of rock. Mission specialist Christina Koch spoke about this afterward. She told President Trump that one of the biggest highlights of the entire mission was coming back from behind the far side and having the first glimpse of Earth again after being out of communication for 45 minutes. She said it reminded her, in a way nothing else could, what a special place they have. That phrasing is worth sitting with. She did not emphasize the science. She did not reach for data or discovery. She talked about seeing Earth again, which means that the 40 minutes without it was significant in ways that go beyond mission parameters. The absence of Earth was psychological. It was existential. It was the sudden and inescapable confrontation with just how far from home they actually were. And yet, the crew kept working. During those 40 minutes of silence, they continued their observations of the far side. They photographed terrain that no human eye had ever directly seen. They described what they were looking at in real time, narrating to audio recorders that could not transmit anything to anyone. Hansen saw 2 of the impact flashes during this period, 2 explosions on the surface below, witnessed by 4 people and by no one else. They also, at some point during the blackout, broke a record that had stood for 53 years. At 7:07 in the evening, still behind the moon, still completely cut off from Earth, the Orion spacecraft reached its farthest point from home, 252,756 miles. That is farther than any human being had ever travelled from the planet on which our species evolved, farther than Apollo 13's harrowing record, set during that mission's desperate slingshot manoeuvre in April 1917. Farther than any person in all of human history, they broke the record in silence. No cheering from Mission Control, no live broadcast to billions of viewers, no moment of acknowledgement from anyone outside the capsule. Just 4 people in the mathematics of orbital mechanics, crossing a threshold that no human had ever crossed before, in a spacecraft floating in the dark behind the far side of the moon. Jeremy Hansen brought maple cream cookies from Canada. The crew ate them together, floating in microgravity, 252,000 miles from home. Wiseman called it surreal. This was not the first time astronauts had experienced this kind of communications blackout. Every Apollo crew that orbited the moon went through it. Apollo 8 in December 1968 was the first. Jim Lovell, Frank Borman, and Bill Anders went behind the moon on Christmas Eve and spent 45 minutes per orbit in complete silence. They orbited 10 times. 10 separate blackouts. 10 separate moments when Mission Control could do nothing but wait. Apollo 13's blackout was different in character, not in duration. The spacecraft was crippled. An oxygen tank had exploded. The crew's survival was genuinely uncertain. When they went behind the moon, no one in Houston knew whether they would come back out the other side alive. The waiting was among the longest minutes in the history of the space program. They came back out. They came home. The Artemis II crew came back out too, at 7:24 in the evening on April 6th. The Deep Space Network reacquired the signal. Data began streaming, screens lit up, voices returned. And outside the windows of the spacecraft, rising above the lunar horizon, was something blue and white and impossibly beautiful. Earth coming back. The photographs do not prepare you for it. This is one of the consistent things the Artemis II crew said about the far side of the moon. They had staged satellite imagery. They had reviewed topographic maps. They had trained using high-resolution data from orbiters that have been mapping the lunar surface in extraordinary detail for years. And none of it fully prepared them for the experience of actually looking at the far side from 4,000 miles above it. Christina Koch reported the colours first. "The more I look at the moon," she said, "the browner and browner it looks." The crew described shades of brown, shades of blue, greenish tones in the highlands, subtle variations that hinted at mineral composition in ways that satellite imagery had not quite captured. 2 observers, looking at the same feature from slightly different angles, sometimes described different colours, which was not a problem. It was exactly the kind of data the science team was hoping for. But the most striking thing about the far side was not any specific colour, and it was not any specific crater. It was an absence. Look at the near side of the moon, the side that faces Earth, and you see the dark patches that people have stared at and named for as long as human beings have been looking up at night. The ancient astronomers called them maria, seas, even though they have never held water. They are vast smooth plains of ancient basalt, lava that poured across the surface billions of years ago and hardened into the dark sheets we see today. The near side of the moon is roughly 31% maria. A third of its surface is covered by these dark volcanic plains. The far side of the moon is less than 1% maria, less than 1%. The far side is almost entirely covered by pale highland terrain, ancient, heavily cratered, battered by 4.5 billion years of continuous bombardment, with almost no volcanic resurfacing to smooth it out. Craters on top of craters, on top of craters, all the way to every horizon. It looks nothing like the moon you see from your backyard, and it looks nothing like any Apollo photograph. The crew was not looking at a familiar object from an unfamiliar angle. They were looking at a genuinely different world. The difference runs deep, literally. The far side crust is up to 20 kilometers thicker than the near side crust. 20 kilometers of additional rock between the surface and the mantle below. When ancient asteroids hammered the far side hard enough to crack the crust, the magma beneath did not have a clear path to the surface. The cracks did not go deep enough. The lava stayed underground, and the surface stayed pale and cratered and ancient. On the near side, the thinner crust cracked all the way through. Molten rock flooded the basins. The dark plains formed. The familiar face of the moon was created. But why is the crust thicker on one side? Why would one hemisphere of a world be substantially different from the other? Not just on the surface, but all the way down into the interior. This is where the science gets genuinely fascinating, and where 2025 brought some of the most significant new evidence in decades. The near side of the moon contains a geological region called the Procellarum Creep Terrain. CREEP is an acronym for potassium, rare earth elements, and phosphorus, a signature of radioactive elements, specifically uranium, thorium, and potassium, that generate heat as they decay. For billions of years, this region functioned as a kind of radioactive furnace beneath the near side. It kept the interior warm, it powered eruptions, it drove the volcanic activity that created the dark plains. The far side had no comparable heat source. It stayed cold, it stayed pale, it stayed cratered. A 2025 study published in the journal Nature by Park and colleagues confirmed this asymmetry using tidal response data. By measuring how the moon deforms slightly under Earth's gravitational pull, they determined that the near-side mantle is measurably warmer than the far-side mantle. This is not a surface phenomenon. It goes all the way down into the deep interior of the moon. The same year, a separate study published in Nature Geoscience took the investigation further, using samples returned by China's Chang'e 6 mission, the first samples ever collected from the far side of the moon. The mission landed inside the South Pole Aitken Basin in June 2024 and returned material to Earth for analysis. The far side lava that did manage to reach the surface, they found, formed at approximately 1,100 degrees Celsius, roughly 100 degrees cooler than the near-side basalts. Professor Yang Liu of University College London described it simply: the two-faced moon. One side ran hot, the other ran cold, and that difference shaped everything. But how did the asymmetry begin? A November 2025 paper in the journal Science by Hopp and colleagues presented new evidence pointing back toward the formation of the moon itself. The leading theory of lunar origin holds that a Mars-sized body called Theia struck the proto-Earth roughly 4.5 billion years ago, vaporizing a significant portion of both bodies and launching a cloud of molten material into orbit. That debris coalesced and cooled over millions of years, becoming the moon. During the moon's early phase, when the entire body was a globe of magma, what scientists call a magna ocean, the radioactive elements appear to have been concentrated on one hemisphere. The mechanism may have involved the gravitational tidal interactions with the nearby early Earth, combined with asymmetric cooling patterns. One side got the uranium and thorium, the other did not. From that moment, roughly 4.5 billion years ago, the moon's fate was determined. The side with the radioactive elements would run hot, erupt, resurface, and show the dark, smooth face we look at tonight from our backyards. The side without them would stay cold, stay pale, stay ancient, and wait 4 billion years for the first human eyes to see it from up close. The Artemis II crew was looking at the outcome of a chemical lottery decided before a single cell had ever existed on Earth. And the Chang 6 data revealed something else about the far side that has immediate consequences for future missions. It is dry. Not dry in the way a desert is dry in a way that approaches the practical limits of measurement. The far side samples contained less than 2 micrograms of water per gram of rock. The near side can contain up to 200 micrograms per gram. The far side is for practical purposes bone dry. Water is the most critical resource for any long-term human presence on another world. It is needed for drinking, for growing food, for manufacturing rocket propellant through electrolysis, split a water molecule into hydrogen and oxygen, and you have both breathable air and the components of a rocket fuel. Without water, a permanent base is entirely dependent on resupply from Earth, which is extraordinarily expensive. The dream of a far-side lunar base, positioned away from Earth's radio interference, ideal for astronomy, the natural location for a deep space radio observatory, runs directly into this practical constraint. The far side has almost no water. And that changes everything about what it would take to put humans there. This is the two-faced moon. Beautiful, ancient, scientifically revolutionary, and, in at least one very practical sense, significantly less hospitable than the side we have always been looking at. Before the mission, NASA's lunar science lead Kelsey Young explained something that sounds simple but carries the entire argument for sending humans to the moon instead of another robot. The human eye, she said, especially when connected to a well-trained brain, is capable of making nuanced color observations in literally the blink of an eye. Observations that no satellite camera, however sophisticated, can fully replicate. Here is the problem that statement is solving. Orbiters like the Lunar Reconnaissance Orbiter have been mapping the moon in extraordinary detail since 2009. We have high-resolution images of nearly every square meter of the lunar surface. We know the topography. We can measure elevation, crater depth, shadow length, and reflectivity with a precision that would have seemed miracle to the Apollo generation. But those images are captured in specific wavelength bands. The camera records light at fixed frequencies, like playing a piano with only certain keys available. The human eye perceives a continuous spectrum, detecting subtle gradations of color that fall between the bands a satellite is designed to measure. And crucially, the human eye adapts in real time to changing lighting conditions. As Orion moved across the lunar surface, the angle of illumination shifted continuously. The same crater would look different from one minute to the next as the sun's light struck it from a new direction. That continuous adaptation, the way a trained brain processes those shifting signals and extracts information, is something orbital cameras simply cannot do. NASA had prepared approximately 35 geological targets for the crew to observe during the flyby. The list included some of the most scientifically significant features visible from the Artemis II trajectory, loaded onto portable computer devices that each crew member carried. The Oriental Basin was the primary target, a nearly 600-mile wide impact crater straddling the boundary between the near and far sides, formed 3.8 billion years ago, retaining dramatic concentric ring structures that remain among the most spectacular impact features in the inner solar system. As Orion approached and then passed Oriental, the crew observed it from continuously changing angles. This parallax effect gave them a three-dimensional sense of the basin structure that no single orbital photograph can provide. Wiseman reported brownish tones in the outer rings. Glover perceived the same features slightly differently, describing subtly different shades. This was the science working as intended. Hertzsprung crater, nearly 400 miles wide, older and far more degraded than Oriental, was another key target. By comparing the two craters side by side, scientists get something extraordinary, a visual record of geological time on a world without weather or plate tectonics. Oriental's rings are still sharp. Hertzsprung's have been softened and battered by billions of years of subsequent impacts. The contrast is a time lapse of 4 billion years compressed into a single observation session. The crew also observed the Glushko crater, 27 miles wide, known for striking white ray streaks extending more than 500 miles across the surface, and the Rhine-Agana swirl, one of the most mysterious surface features on the entire moon, which we will return to later. The crew worked in pairs, 2 astronauts at the windows for 55 to 85 minutes, observing and narrating, the other 2 communicating with mission control, exercising or resting. Then they switched. The narrations were continuous, real-time, the crew describing what they saw in the moment, not from a script. And to keep their eyes adapted to the subtle colour variations on the surface, they improvised. They draped a t-shirt over one of the cabin windows to block stray light from inside the spacecraft. It worked, mostly, except that it caused condensation problems, and they had to use a condensation hose to dry things out. Glover noted that switching between the dark cabin, his dimly lit tablet screen, and the bright lunar surface was physically taxing on his eyes. This is what doing science in a small capsule 250,000 miles from home actually looks like. Not the clean choreography of a simulated mission, not the seamless efficiency of a robotic orbiter, improvised equipment made from available t-shirts, condensation problems, tired eyes. Real human beings trying to do rigorous science under conditions that combine genuine wonder with the constant small complications of living in a can in space. And yet it worked. After the flyby, Young told the crew she could not say enough about how much science they had already provided. Not just data, but inspiration. She told them they had brought the moon closer. That phrase captures something important. Robots collect data. Humans collect meaning. And sometimes the meaning is what matters more, not just emotionally, but scientifically, because meaning is what tells you which data to look for next. Victoria Glover became obsessed with the Terminator, not in the science fiction sense. The Terminator, in planetary science, is the dividing line between the illuminated and dark sides of a world, the edge where sunlight ends and shadow begins. From Earth, the lunar Terminator looks like a smooth curve sweeping across the disk. From 4,000 miles above the surface, it looks like something else entirely. Glover radioed mission control and said he wished he had more time to simply sit and describe what he was seeing. He called it fantastic. The most rugged Terminator he had ever seen from a lighting perspective. And then he said something that made the science team lean forward. There were islands out there. Islands of terrain, completely surrounded by darkness, indicating dramatic variations in elevation that the angle of illumination was revealing in real time. Hansen added his own description. When you look at the Terminator, he said, it is just impossibly rugged, and it reminds you that the whole far side is that way. What the crew was seeing is a phenomenon well understood in photography and geology, but rarely experienced so viscerally. At the Terminator, the sun sits right on the horizon from the perspective of anyone standing on the surface below. Light arrives at an extreme angle, almost parallel to the ground. When illumination strikes a surface from that angle, it casts enormously long shadows. Every ridge, every hill, every crater rim projects a shadow that stretches across the landscape like a pointing finger. Features that would be invisible under overhead sunlight leap out in three-dimensional relief. Subtle fractures, micro-ridges, ancient collapsed lava tubes, tiny elevation changes, all of them suddenly visible because the light is coming from the side rather than from above. This is why orbital cameras miss things that human eyes catch. Satellites photograph the moon from directly above. From that perspective, short shadows can be lost entirely in the resolution of the image. But from the Terminator angle, the long shadows expose the true texture of the surface. The Terminator is a revealer, stripping away the moon's deceptively smooth appearance to show what is actually underneath. And what is underneath, on the far side, is chaos. Ancient, accumulated, relentless chaos. The product of 4.5 billion years of impacts, with nothing to smooth them out. Glover described it as going science fiction. After everything else they had seen, he told Mission Control, the Terminator took the visual experience somewhere beyond what he had words for. Koch added an observation with direct scientific weight. The bright young craters visible near the Terminator, she said, looked like a lampshade with tiny pinprick holes in it, with a light shining through. They were dramatically brighter than the surrounding terrain. Those bright craters are geologically fresh. Their ejecta, the material blasted out during the impact that formed them, has not yet been darkened by space weathering. On the Moon, space weathering is a slow process in which solar wind particles and micrometeorite impacts gradually alter the surface material over millions of years, darkening and reddening it. Fresh craters have bright white ejecta that slowly fades to match the surroundings. The distribution and brightness of these fresh craters carries information about recent impact rates and the rate at which the surface weathers, data that feeds directly into models of lunar evolution. And then Glover reported something that surprised even the science team. Some mountain peaks near the Terminator were so bright they appeared to be covered in snow. They were not, of course. The Moon has no water in any form visible to the naked eye across its general surface. What Glover was seeing was unweathered rock, likely andesite, the pale plagioclase feldspar material that makes up the ancient lunar highlands, reflecting sunlight at a grazing angle with extraordinary brilliance. The contrast between these white peaks and the absolute black of the valleys below created a visual effect so extreme it had no analogy in any previous lunar imagery. Which is precisely the point. Every photograph you have ever seen of the Moon was taken under specific lighting conditions from a specific angle. None of them were taken from 4,000 miles above the surface at this particular angle during this particular geometry. The crew was seeing something genuinely new. Not new in the sense that the Moon had changed, but new in the sense that no instrument had ever captured this exact perspective before. Kelsey Young's response to Glover's description was undisguised excitement. She told him it was an amazing picture he had just painted. She said she had literally seen fist pumps in the air in the science evaluation room. These types of observations, she said, are things that humans are uniquely able to contribute. that is the answer to why we send people. Shortly after breaking the Apollo 13 distance record, while the crew was still working through their observation targets, Jeremy Hansen took the microphone. His voice was steady, at first, professional. The measured calm that astronauts are trained to maintain during live transmissions. A number of years ago, he said, we started this journey, and in our close-knit astronaut family, we lost a loved one. He paused. Her name was Carol, the spouse of Reed, the mother of Katie and Ellie. Carol Taylor Wiseman was a neonatal intensive care nurse. She spent her career at the Children's Hospital of the King's Daughters in Norfolk, Virginia, and later as a school nurse in Maryland and Texas, moving wherever her husband's career with NASA took their family. She was born in Virginia Beach. She was 46 years old when she died of cancer in 2020. Commander Reed Wiseman has been raising their two daughters alone since then. While scanning the lunar surface during the observation period, the crew had identified two small craters that had never been formally named. On the Moon, fresh is a relative term. A fresh crater can be millions of years old. What it means is that the crater still shows bright ejecta that has not yet been darkened by space weathering. These craters stood out against the older, darker surface, like white spots on grey paper. The first, located just northwest of the Oriental Basin, the crew wanted to name Integrity after their spacecraft. The name embodied, Wiseman would later explain, the foundation of trust and candor and humility that had defined years of preparation and the mission itself. The second sat on the boundary between the near and far sides, near the Glushko crater, on the same latitude as the Meteors crater. It was visible as a bright spot from Earth at certain points during the Moon's transit. Hansen described its location. And then he said the words that stopped Mission Control cold. It is a bright spot on the Moon, he said, and we would like to call it Carol. As he spoke, Wiseman reached over and put his hand on Hansen's shoulder. His eyes were wet. He pressed his lips together and nodded. Then the two men embraced. Not a formal handshake, not a professional pat on the back, a real hug. The kind of hug that happens when grief and love and distance collide all at once. And then Koch and Glover joined them. All four astronauts pulled together in a floating embrace, 252,000 miles from Earth, wiping tears, holding each other in the silence of deep space. Mission Control went quiet. The science team watched. The flight controllers watched. The families in the viewing gallery watched. Nobody spoke. The moment belonged to the crew and to a woman who was not there. Carol Wiseman did not get to see her husband launch. She did not get to watch him fly. She did not get to hear him describe the far side of the Moon, or the impact flashes, or the corona wrapping around the sun. But if the International Astronomical Union approves the names, then the formal submission was made after the mission concluded, there will be a bright spot on the Moon called Carol, a spot visible from Earth, a spot their daughters can look up and find on a clear night and know that their mother's name is written on another world. The internet responded the way it sometimes does when something real breaks through the noise. One comment, sounds like Carol was loved to the moon back, literally. Another, her babies can look to the night sky and see their mum. This moment matters for reasons that extend well beyond the personal. It is the argument for sending humans into space, distilled into a single act. Robots do not name craters after people they have lost. Robots do not weep. Robots do not form a floating embrace while tears cling to their cheeks in microgravity. The emotional resonance of Artemis II is not a byproduct of the science. In many ways, it is the science. It is what makes the world care. It is what turns a flyby into a cultural event that billions of people follow in real time. Numbers and data fill journals. Moments like this fill hearts. And hearts are what sustain the will to fund the next mission. NASA's biography of Wiseman notes that he considers his years as a single parent the most meaningful of his life. He did not step back from the astronaut corps after losing Carol. He trained harder. He prepared more thoroughly. He flew. And when he arrived at the moon, the first act he chose to perform, with the freedom to name a landmark, was to honour the woman he lost. That is not sentiment. That is character. And character cannot be uploaded to a satellite. Among the 35 targets the Artemis II crew observed during the flyby was a feature that has baffled scientists since the 160s. It is called Rhina Gamma. It sits on the vast dark lava plain called Oceanus Procellarum on the near side of the moon, and it looks like nothing else on any world we have ever studied. It is a bright, tadpole-shaped marking on the surface, not a crater, not a deposit, not a flow of different material. It is a swirl, a pattern of brightness that has no obvious geological origin. The crew flew over it during the near-side approach phase of the flyby and observed it from an angle and under lighting that no previous satellite pass had replicated exactly. The descriptions they provided will be analysed for months. But the deeper mystery of Rhina Gamma goes far beyond what any single observation can resolve. Because Rhina Gamma is not just a bright spot, it sits directly on top of one of the strongest magnetic anomalies on the moon. This is where the story becomes genuinely strange. The moon has no global magnetic field, not anymore. Earth has one, generated by the churning of molten iron in the outer core, a process called the geodynamo. That magnetic field wraps around our planet, deflects solar wind particles, and protects us from the constant bombardment of charged particles streaming outward from the sun. The moon once had a similar field, billions of years ago, when its interior was hot enough to sustain a dynamo. But as the moon cooled and its core solidified, the dynamo died. The global field collapsed. The moon became magnetically naked. Except it is not entirely naked. Scattered across the lunar surface are dozens of localized magnetic patches, small regions where surface rocks retain a magnetic signature, like a tattoo left behind by a field that no longer exists. These anomalies are weak by terrestrial standards, typically a few hundred nanoteslas compared to Earth's 50,000, but they are measurably there. And many of the moon's bright swirls, including Rhina Gamma, sit directly on top of them. The leading explanation is called the magnetic sunscreen hypothesis, and it is as elegant as it is counterintuitive. The sun constantly sends a stream of charged particles outward through the solar system, the solar wind. On Earth, the magnetosphere deflects most of this stream. On the moon, which has no global field, the solar wind strikes the surface directly. Over millions of years, this bombardment alters the surface material. It darkens it. It changes the chemical bonds. It shifts the reflectivity. This is space weathering, while the moon's general surface is dark and grey. But where a localized magnetic anomaly exists, the field, even though it is weak, can deflect some of the incoming solar wind particles. The surface beneath the magnetic patch receives less bombardment, less weathering, less darkening. It stays brighter. The result is a visible bright marking on the surface that corresponds to the shape and extent of the underlying magnetic field. A 2018 study, published in Communications Physics, modelled the magnetic field around Rhina Gamma and found that it is the right shape and strength to produce exactly the observed swirl pattern. The model works. The deeper question is where these magnetic anomalies came from in the first place. 3 competing explanations have been proposed. The first suggests that cometary impacts deposited magnetized material onto the surface. The second involves basin-forming impacts. When enormous asteroids struck the early moon, they launched iron-rich ejecta across the surface. If this material cooled in the presence of the moon's ancient magnetic field, it would lock in a permanent magnetic signature. The magnetic anomalies would be fossils, records of impacts from a time when the lunar dynamo was still active. The third explanation, proposed in a 2024 study in the Journal of Geophysical Research Planets, points to high titanium magma cooling underground. Iron titanium oxide minerals that crystallize slowly beneath the surface can carry an intense magnetic signature, especially if the crystallization occurred while the moon's ancient field still existed. In this model, the magnetic anomalies are underground magnets buried deep in the crust, projecting their fields upward through miles of rock. In February 2026, researchers from Oxford published findings that helped clarify the timeline of the moon's magnetic history. Previous studies have produced contradictory results. The Oxford team showed that both sides of the debate were partially correct. The field operated in multiple phases at different intensities, before finally dying out approximately 1 billion years ago. The magnetic tattoos on the surface are records of that complex history, written in iron and frozen in time. NASA has a dedicated mission planned to investigate Rhina Gamma up close. The Lunar Vertex mission would send a lander and small rover directly into the swirl to take the first surface-level magnetic measurements. The mission has been rescheduled but remains a scientific priority. Until it arrives, the swirl keeps its secrets. A bright brushstroke on a dark canvas. A message written in magnetic ink by a process that science is still learning to read. Apollo 11. July 16, 1969. Buzz Aldrin is floating in the command module in the dark, eyes closed, trying to sleep, and he sees a flash, not through the window, not from an indicator light, inside his eye. A brief streak of white light that appears and disappears in less than a second. He opens his eyes. The cabin is dark. Nothing has changed. He closes his eyes again. Another flash. Every subsequent Apollo crew reported the same experience. Apollo 12, 13, 14, 16, 17, 17. Every astronaut who travelled beyond Earth orbit and spent time in darkness saw the flashes. They came in 3 forms: spots, brief pinpoints of light; stars, slightly larger and longer lasting; and streaks, lines of light that traced across the visual field and vanished. Most were white or colourless. Apollo 14 astronaut Edgar Mitchell reported one that was blue, with a white cast, like he said, a blue diamond. The astronauts were not hallucinating. They were being shot. The explanation is cosmic rays, high-energy charged particles, mostly protons and atomic nuclei, produced by some of the most violent events in the universe: supernovas, black holes, the shock waves of colliding galaxies. These particles are accelerated to velocities approaching the speed of light and flung across the cosmos. They travel for millions of years before some of them find their way into our solar system. On Earth, we are largely protected by 2 shields. The first is the magnetosphere. the magnetic field generated by our planet's iron core, which extends thousands of miles into space and deflects the majority of incoming charged particles. The second is the atmosphere itself, which absorbs most of what gets through the magnetic field. Below these two layers of protection, cosmic ray bombardment is reduced to a level the human body can tolerate across a normal lifetime. The Moon sits outside Earth's magnetosphere for most of its orbit, and the Moon has no magnetic field of its own, no atmosphere, no protection. The Artemis II crew, travelling between Earth and the Moon, passed through the Van Allen radiation belts and then entered the completely unshielded environment of deep space. Out there, cosmic rays pass through everything: the spacecraft walls, human bodies, and human eyes. The leading explanations for the light flashes involve three possible mechanisms. The first is Cherenkov radiation. When a charged particle travels through a medium faster than the speed of light in that specific medium, light travels slower through the vitreous humour of the eye than through vacuum. It produces a brief flash of bluish light. This is the same phenomenon that produces the eerie blue glow in the water surrounding nuclear reactors, where electrons travel faster than light moves through water. The second mechanism is direct ionization of retinal cells. The cosmic ray particle passes through the retina and deposits enough energy to trigger the photoreceptor cells, causing them to fire as if they had been struck by actual light. The brain receives the signal and interprets it as a flash. The third mechanism involves direct interaction with the optic nerve or even the visual cortex of the brain itself. A cosmic ray passing through the skull and interacting with neural tissue responsible for processing vision could produce the sensation of light without ever touching the eye. During Apollo 16 and 17, NASA tested this directly. They built a device called ALMME, the Apollo Light Flash Moving Emulsion Detector, a helmet containing photographic emulsion plates that would record the tracks of cosmic ray particles passing through it. The astronaut wearing it would report flashes while the emulsion recorded particle tracks. Results were suggestive but limited. 2 out of 15 recorded particle tracks coincided with flash reports. Not conclusive, but consistent with the hypothesis. The health implications extend beyond the visual curiosity. Studies of Apollo astronauts have shown they were significantly more likely to develop cardiovascular disease than astronauts who never left low Earth orbit. A sample size of only 24 people, all male, all Apollo, but a consistent statistical pattern. Studies on mice exposed to simulated galactic cosmic ray environments have shown cognitive decline, increased anxiety, and impaired memory formation. A January 2026 article in the journal Science detailed the radiation environment awaiting the Artemis astronauts beyond Earth's magnetosphere: Van Allen belt exposure during transit, unpredictable solar particle events that can spike to dangerous levels within hours, and the constant background rain of galactic cosmic rays arriving from all directions without warning or pattern. For Artemis II's 10-day mission, the accumulated dose is manageable within accepted health frameworks. The future missions, a 6-month surface stay, a return to the Moon for a full scientific expedition, and eventually a 2 to 3 year journey to Mars will require either substantially better shielding solutions or a full rethinking of how we protect human beings in deep space. The flashes the Apollo astronauts saw are not just a curiosity. They are a symptom, a visible, perceptible demonstration of invisible damage. Every flash is a cosmic ray particle passing through an astronaut's head at nearly the speed of light. depositing energy, breaking molecular bonds, and moving on. You can see the damage as it happens. You simply cannot stop it. At 7:24 in the evening on April 6th, Orion emerged from behind the moon. The crew watched Earth rise above the lunar horizon. It was not the first time human beings had seen this, but it was the first time in more than 53 years, and it was the first time from this particular altitude, on this particular trajectory, under this particular geometry. The crew was farther from the moon and at a different angle than any Apollo spacecraft had flown. The perspective was genuinely unique. Earth and moon in the same frame, seen from a vantage point that had never existed before in human history. The history of this specific image of Earth seen rising over the lunar horizon begins on Christmas Eve 1968. Apollo 8 was not a landing mission. It was an orbiting mission. Go to the moon, circle it 10 times, come home. Frank Borman, Jim Lovell, and Bill Anders launched on December 21st. On their fourth orbit, as the spacecraft came around the far side and the lunar horizon swept into view, Bill Anders looked out the window and saw the Earth rising above the edge of the moon. Blue and white against the absolute black of space, hanging above the barren grey surface below. He reached for a camera. The first shot was black and white. He swapped to colour film and took the photograph that would become the most reproduced image in the history of exploration, Earthrise. Nature photographer Galen Rowell called it the most influential environmental photograph ever taken. Time included it in the list of the 100 most influential photographs in history. Bill Anders himself said the image undercut his religious beliefs, which he described not with distress, but with the particular clarity that comes from seeing something so overwhelming that previous frameworks simply stop applying. The paradox of the mission was plain. They went to the moon to explore the moon, and what they found was Earth. Not new information about Earth, but a new way of seeing it, a perspective that made all borders invisible, all conflicts small, all divisions irrelevant. A small bright sphere alone in the dark, the only home of everything alive. 58 years later, the Artemis II crew felt the same shift. Victor Glover broadcast from the spacecraft, "Trust us. You look amazing. You look beautiful. You also look like one thing. Homo sapiens is all of us. No matter where you are from or what you look like, we are all one people." Jeremy Hansen said it more quietly. "Right away, you are humbled. The fact that 4 of us get to be out here just brings you to your knees." Scientists and psychologists call this the overview effect, a term coined by space philosopher Frank White in 1987 to describe the cognitive shift that astronauts experience when they see Earth from space. It is not simply awe, though awe is part of it. It is a fundamental change in perspective. The borders disappear, the conflicts shrink, the planet looks like what it is, a single system, a single organism, a single fragile home. The crew carried something with them that made the connection to Apollo 8 tangible and deeply personal. Before the mission, they had been given the original Apollo 8 Silk mission patch that had flown with Jim Lovell to the moon in December 1968. They brought it aboard Orion. The patch had now travelled to the moon twice, once in 1968 and once in 2026, carried by different hands but on the same journey. And Lovell himself had one final connection to offer. 2 months before his death, in August 2025, at the age of 97, Jim Lovell recorded a wake-up message for the Artemis II crew. Mission Control transmitted it up to the spacecraft on the morning of the flyby. Hello, Artemis II. This is Apollo astronaut Jim Lovell. Welcome to my old neighbourhood. It is a historic day, and I know how busy you will be, but do not forget to enjoy the view. The crew listened to the voice of a man who had seen Earthrise on Christmas Eve 1968, who had nearly died trying to get home from the moon in 1970, who had watched the entire arc of human space exploration across a lifetime of 97 years, and who understood better than almost anyone alive what the Artemis II crew was about to experience, because he had experienced it first. Wiseman's response was quiet. It is just a real honour to have that on board with us. Let us go have a great day. The Oriental Basin was the primary geological target of the Artemis II flyby. Nearly 600 miles wide, formed 3.8 billion years ago, Oriental straddles the boundary between the near and far sides of the moon. When the object that created it struck, an asteroid or comet of truly extraordinary size, the energy released sent shockwaves rippling outward through the crust in concentric rings, like the rings that expand when you drop a stone into still water. Those rings are still there, preserved in rock, the Cordillera Mountains on the outside, the outer Rook Mountains in the middle, the inner Rook Mountains closest to the centre, nested one inside the other in a structure of almost geometric precision. As Orion moved across the basin, the crew observed it from continuously changing angles. The parallax, the way the relative positions of foreground and background features shift as your viewing position moves, gave them a three-dimensional sense of the basin's structure that no single orbital image can replicate. Wiseman reported brownish tones in the outer rings. Glover perceived them slightly differently. The colour discrepancy was not a problem. It was exactly the kind of data the science team needed. Oriental is scientifically important because it is the youngest large basin on the near side. It is the best preserved example of what happens when a very large object strikes a world with no atmosphere, no liquid water, and no plate tectonics to erase the evidence over time. Every detail of the impact process, how the shockwave propagated, how the crust fractured and rebounded, how molten material flowed and cooled, is still visible in the structure of the rings. Beyond Oriental, on the far side, the crew observed Hirschsprung crater, nearly 400 miles wide, dramatically older, its ring structures battered and softened by billions of years of subsequent bombardment. The contrast between the two craters is a visual time-lapse of geological aging on a world where time is preserved almost perfectly. On Earth, a feature this old would have been erased by erosion, burial, and plate tectonics long ago. On the Moon, it simply degrades slowly, one impact at a time, accumulating the scars of geological time without ever quite losing them. But the most significant basin in the region, even though the Artemis II trajectory only allowed a brief glimpse of it, is neither Oriental nor Hirschsprung. It is the South Pole Aitken Basin, and it is one of the most extraordinary features in the entire solar system. Approximately 1,550 miles across and 5 miles deep, the SPA Basin is among the largest confirmed impact structures anywhere in the known solar system. To put the scale in terms that the mind can grip, it is wider than the distance from New York to Denver and deeper than any ocean trench on Earth. When the object that created it struck, something of truly planetary scale, it may have punched entirely through the lunar crust and into the mantle below. The basin floor may contain exposed mantle material, rock from deep inside the moon that was blasted to the surface by the force of the impact. If scientists can analyze those rocks in detail, they gain access to the lunar interior in a way that surface sampling cannot provide. The mantle's composition, the moon's thermal history, the conditions of the inner solar system during the period of heavy bombardment, roughly 4 billion years ago, all of this is potentially encoded in the SPA basin floor. China's Chang'e 6 mission did exactly that. In June 2024, it landed inside the SPA basin and collected the first samples ever returned from the far side of the moon. The results, published in Nature in July 2025, across 4 separate papers, were revelatory. The far side mantle is what geochemists call extremely depleted in incompatible elements, elements that concentrate in liquid magma during melting and tend to mark a geologically active interior. On the near side, these elements are abundant, part of the creep signature driving volcanic activity. On the far side, they are almost absent. And then the water data. Less than 2 micrograms of water per gram of rock. Against the near side's potential, 200 micrograms per gram. The SPA basin is dry, the far side is dry, and for the humans who are planning to return to the moon, not for a brief visit, but for extended stays, the location of water on the moon is not an abstract scientific question. It is an operational constraint of the first order. This is why the lunar South Pole has become the focus of the next generation of missions. The South Polar regions contain permanently shadowed craters, areas that sunlight has not reached for billions of years, where temperatures can fall below -230 degrees Celsius. Cold enough to preserve water ice delivered by comets and asteroids over geological time. Multiple spacecraft have detected signatures consistent with water ice in these shadows. If the ice is there in usable quantities, it changes the economics of lunar exploration completely. Artemis II plans to land astronauts near the South Pole, in part to investigate these ice deposits. That mission will determine whether humanity's next steps on the moon are supported by local resources or depend entirely on resupply from 240,000 miles away. The Artemis II crew's brief view of the SPA basin and the context provided by the Chang'e 6 data together paint a picture of the moon's interior that no previous mission had been able to produce. A two-faced world, warm on one side and cold on the other, wet on one side and dry on the other, volcanically active on one side and geologically frozen on the other. And waiting, in the shadowed craters of the South Pole, the possibility that its own water could be the key to everything. On Earth, a total solar eclipse is among the most powerful experiences a human being can have. It lasts minutes, sometimes less. The sky darkens mid-afternoon, the temperature drops, the birds go quiet. The corona appears, the sun's outermost atmosphere, usually invisible, suddenly blazing around the black disk of the moon. And then, in a few minutes, it is over. People travel thousands of miles for those few minutes. They weep. They describe it, afterward, as one of the most significant experiences of their lives. Now, take that experience and multiply it by 30. At 8:35 in the evening on April 6, 2026, from the perspective of the Orion spacecraft, the sun began sliding behind the moon. For the first 2 minutes, the crew wore eclipse glasses to protect their eyes from the partial phase, as the solar disk was still partially exposed. Then, the moon slid fully over the sun. The disk disappeared. The corona appeared. Reed Wiseman spoke first. It is indescribable. No matter how long we look at this, our brains are not processing the image in front of us. It is absolutely spectacular. Surreal. There are no adjectives. I need to invent some new ones. Glover followed. Humans probably have not evolved to see what we are seeing. It is truly hard to describe. It is amazing. On Earth, totality ends quickly because the moon's shadow moves across the ground at roughly 1,000 miles per hour. You stand in one place and the shadow sweeps past you. From Orion's perspective, the geometry was completely different. The spacecraft was moving in roughly the same direction as the lunar shuttle to level back or ride for the cold of the right side fly, and held. Totality lasted from 8:35 to 9:32 in the evening. 57 minutes. Nearly an hour of the sun completely blocked by the moon. The longest eclipse any human being has ever witnessed. The corona, usually visible only during the few minutes of totality on Earth, was continuously visible for nearly an hour. The crew described it in detail: streamers, long structures of solar material extending outward from the sun, like luminous filaments. Gludder found the metaphor that captured it. "If you've ever seen the spotlight rising from the top of the Luxor Hotel in Las Vegas," he said, "this looks like what that wants to be when it grows up." The Luxor spotlight is a 42 billion candle power beam, visible from space. Glover was saying the solar corona made it look like a fleshlight. During the eclipse, several additional observations emerged. Multiple planets became visible simultaneously: Venus, Mars, Saturn, Mercury, visible as bright points against the darkened sky. Hansen noted that the sun's light was illuminating the entire perimeter of the moon during totality, highlighting topographic features along the lunar limb from an angle no photographer on Earth had ever captured. The crew also observed 2 meteors, not impact flashes on the surface, but actual streaks of debris in space, visible against the darkened sky during totality. And then there was the Earthshine. Wiseman said he had not anticipated it. He had not expected just how much light would still be illuminating the moon. The source was not the sun, it was Earth. Our planet's daytime side reflects sunlight outward into space, and some of that reflected light travels to the moon. Normally this Earthshine is difficult to see because the sunlit portions of the moon are so overwhelmingly bright. But with the sun blocked and the crew's eyes fully adapted to the darkness, Earthshine was startlingly, almost shockingly present. Blover described it: "The Earth is so bright out there, and the moon is just hanging in front of us, this black orb." He reported that Earthshine was bright enough that he could make out surface features on the night side of the moon. The reflected light of our own planet was illuminating another world with enough clarity to see detail from thousands of miles away. Think about what that means. With the sun blocked, the moon was being lit by Earth. The light coming from our planet reflected sunlight, yes, but sunlight that had bounced off the oceans and clouds and continents of home was painting the lunar surface in a faint blue-white wash. Visible to the naked eye from 250,000 miles away, the Earth was still there, still present, still reaching across the darkness to touch the moon, even when the sun could not. The eclipse ended at 9:32. The sun reappeared from behind the moon. The crew put their eclipse glasses back on. Kelsey Young radioed up one final time. "I cannot say enough how much science we have already learned. You really brought the moon closer for us today." And then, from capsule communicator Jenny Gibbons, a message from all the flight controllers in Houston. They had flipped their mission patches around. "Fast class. Welcome, welcome." On one side was the Artemis II logo, with Earth in the foreground and the moon in the distance. They turned them over, moon in front, Earth behind. "We are earthbound," Gibbons said, "and ready to bring you home." There is a conversation about the far side of the moon that goes beyond geology and mission planning. The far side is the only place in the accessible solar system that is permanently shielded from Earth's radio emissions. Our civilization generates electromagnetic noise across a vast range of frequencies, billions of devices, billions of transmissions, an inescapable radio bubble that fills the inner solar system with artificial signals. For radio astronomers trying to observe the universe at low frequencies, this noise is a constant problem. The far side of the moon, by contrast, faces permanently away from Earth. Any radio telescope placed on the far side would have 4,000 miles of lunar rock between it and every artificial transmission humanity has ever produced. It would operate in a silence that no telescope anywhere on Earth, in Earth orbit, or even at the Lagrange points, can replicate. No frequency radio astronomy, frequencies below about 30 MHz, is almost impossible to do from Earth or Earth orbit because the ionosphere absorbs or reflects these wavelengths. But these frequencies carry information about the universe's earliest epochs, about the period before the first stars formed, when hydrogen gas filled the cosmos and its faint 21 centimeter emission signal drifted across billions of light years. The far side of the moon could, in principle, post a radio telescope sensitive to these early signals, capable of seeing back toward the beginning of the universe in a frequency range that has been effectively invisible to every observatory ever built. This is one of the reasons scientists have been dreaming about a far-side observatory for decades. The science case is extraordinary, but the practical case runs directly into the water problem. No water means no long-term habitation without continuous resupply. An automated far-side radio observatory might be achievable. China's Qiuqiao relay satellite, launched in 2018 to enable communication with the Chang'e 4 lander on the far side, demonstrated that the communication challenge can be solved. But a human presence on the far side, sustained over years without access to local water resources, remains a significantly more difficult proposition. The Artemis II flyby provided something important in this context. The crew's direct visual observations of the far side, under lighting conditions and from viewing angles that no satellite had replicated, will help planners understand the terrain in ways that satellite data alone cannot. Every description, every color observation, every note about a geological feature builds toward the detailed knowledge needed to eventually put hardware down there. The far side of the moon is scientifically extraordinary in two directions simultaneously. Looking down at the ancient battered surface, it preserves a record of the early solar system that the near side has largely overwritten. Looking up, shielded from Earth's electromagnetic noise, it offers a view of the universe that no other location in the accessible solar system can match. What the Artemis II crew saw from their window is the beginning of the scientific case for being there. Jim Lovell flew to the moon twice. The first time was December 16th, 1968, Apollo 8, Christmas Eve. He and Frank Borman and Bill Enders circled the moon 10 times, read from the Book of Genesis during a live broadcast seen by a larger audience than any television event in history to that point, and came home having seen something that changed them irreversibly. The second time was April 17th, 1970, Apollo 13. An oxygen tank exploded 2 days into the mission, crippling the spacecraft. The crew used the lunar module as a lifeboat. They swung around the far side, using the moon's gravity to fling them back toward Earth. During that maneuver, they held the distance record for human travel from Earth, 248,655 miles, for 56 years. They made it home, barely. Lovell lived another 55 years after Apollo 13. He watched the shuttle program and the building of the International Space Station and rovers on Mars and the slow construction of the Artemis program. He watched an entire generation pass through adulthood, never seeing a human being travel beyond low Earth orbit. He watched the moon become a memory. 2 months before his death in August 2025, at 97 years old, he recorded the message that Mission Control played for the crew on the morning of the flyby. The message was 40 seconds long. It is a measure of what Lovell understood about the experience the crew was about to have, but he did not fill those 40 seconds with facts, or historical context, or technical congratulations. He welcomed them to his old neighbourhood. He acknowledged the historic day. He told them he knew how busy they would be, and then he said the only thing that needed saying: do not forget to enjoy the view. That sentence is not small talk. It is the distilled wisdom of a man who had orbited the moon on Christmas Eve, who had watched Earth rise over the lunar horizon with his own eyes, who had nearly died in space, and spent 55 years living with what he had seen. It is the wisdom that comes from knowing that no amount of mission data captures what it means to actually be there. Enjoy the view. Not because the view is more important than the science, not because wonder is more valuable than data, but because the view changes you in ways that the data cannot, and the change is the part that matters most when you come home. The Artemis II crew was different from the Apollo crews in every measurable demographic sense. Christina Koch, the first woman to travel beyond Earth orbit. Victor Glover, the first black astronaut on a lunar mission. Jeremy Hansen, the first non-American to reach the moon. Reed Wiseman, an American commander and single father raising 2 daughters. This matters not as symbolism, but as science. Different people see differently. They notice different things. They make different connections. A crew that looks more like the world brings more perspectives to what they observe, and more of what they see reaches audiences who might not otherwise feel a visceral connection to exploration that drives public support for missions. Glover, broadcasting from the spacecraft, we call amazing things that humans do moonshots for a reason. Because this brought us together and showed us what we can do when we not just put our differences aside, when we bring our differences together. Hansen, at the moment of breaking the Apollo 13 distance record, we most importantly choose this moment to challenge this generation and the next to make sure this record is not long-lived. Not to celebrate the record, to challenge the future, to break it. That distinction matters enormously. Hansen was not commemorating an achievement. He was issuing an invitation. Every record in the history of human exploration has existed to be broken. The whole point of going as far as you can go is not to stop there. The data from Artemis II will be analysed for months. The crew's photographs and verbal descriptions will be compared with satellite imagery. The impact flash reports will be cross-referenced with citizen science observations from Earth-based monitors. The colour observations of the far-side terrain will feed into new models of mineral composition. The Terminator descriptions will refine understanding of surface texture at scales orbital cameras cannot resolve. The scientific return from a 7-hour flyby, conducted by 4 trained human observers with improvised equipment and tired eyes, will take years to fully process. But there is a different kind of data that does not require months of analysis, because it arrived in real time, unfiltered, in the words of the people who were there. Wiseman, there are no adjectives. I need to invent some new ones. Glover, humans probably have not evolved to see what we are seeing. Koch, humility. Hansen, make sure this record is not long-lived. And Lovell, from beyond the grave, do not forget to enjoy the view. These are not supplementary to the scientific results. They are themselves a kind of data about what it means to be a human being and see something that no human being has seen before. About the relationship between experience and knowledge. About what we lose if we send only robots. The moon is 238,900 miles away. It has been exactly that far, on average, for the entire existence of our species. It does not care about us. It sits in its orbit, tidally locked, absorbing impacts by the millions, grinding them into its surface, wearing the scars of 4.5 billion years of cosmic violence without complaint. It has been patient in a way that nothing human can comprehend. What is fragile is us. Not in the romantic sense, not fragile as in delicate or precious, but fragile in the precise physical sense of existing within extraordinarily narrow parameters. Our planet maintains liquid water because it sits in a specific narrow band of distance from a specific kind of star. Our atmosphere maintains the right composition because of a complex system of geological and biological feedbacks that have been operating in ref equilibrium for hundreds of millions of years. Our civilization exists because a series of stable conditions, climatic, ecological, political, technological, have been maintained across long enough timescales for knowledge to accumulate. From the surface, that maintenance feels permanent. It feels like the default state of things. From the moon, it does not. From the moon, Earth looks like what it is, a thin film of atmosphere clinging to a rock. A pale blue dot with a membrane of air and water so thin that at this distance you could cover it with your thumb. The only home, the only one. Every astronaut who has ever seen Earth from space describes the same thing. The borders disappear. Not metaphorically, literally, visually, actually. The lines that divide nations are not visible from this distance. The conflicts that dominate the daily news are not visible. The arguments that consume enormous amounts of human energy and attention are invisible. What remains is the planet itself, blue and white and impossibly bright against the black. A single system, a single home, shared by everything alive. The Artemis II crew saw 6 explosions on the moon and came back to tell us that the surface of our nearest neighbour is a continuous shooting gallery that we will have to learn to live with if we want to stay there. They saw the two-faced moon and came back with the first direct human visual evidence of one of planetary science's most persistent mysteries, why one hemisphere ran hot and the other ran cold, and what that asymmetry means for every future mission. They saw the Terminator and described features no satellite image had quite captured. Mountain peaks so bright they appeared snow-covered, valleys so dark they formed lakes of shadow. The relentless cratered texture of the far side revealed in 3-dimensional clarity. They saw the eclipse, 57 minutes of totality, the corona wrapped like white fire, earthshine painting the lunar night side with the reflected glow of home. They saw Earthrise. They named a crater Carol. They ate maple cream cookies in the dark behind the far side of the moon, while rocks exploded below them, and the Earth was hidden behind 4,000 miles of rock, and they were more alone than any 4 human beings had ever been, and they were okay. More than okay, they were transformed. This is what the Artemis II mission was, really. Not a flyby, not a technology demonstration, not a step along a roadmap to eventual permanent lunar presence, though it was all of those things. It was a reminder that the moon is real, and the distance is real, and the silence is real, and that going there, actually going there, with human eyes and human hands and human grief and human wonder, does something that no amount of satellite data can replicate. It changes the people who go, and through them, it changes the rest of us. The next missions will go further. Artemis II will land on the surface near the South Pole. Astronauts will walk on the moon for the first time since December 1972. They will search for water ice in permanently shadowed craters. They will drill into the regolith and collect samples and deploy instruments. They will stay for days rather than hours. Artemis IV will build the Lunar Gateway, a space station in lunar orbit, a permanent staging point for surface missions, the beginning of sustained infrastructure around the moon. And beyond that, the long road to Mars. Each step requires what came before. Artemis II proved the Orion spacecraft can carry humans to the moon and return them safely. It proved the Deep Space Network can manage the communications geometry. It proved the heat shield survives re-entry. It proved the mission architecture is sound. And it proved something that no engineering test can measure. It proved that going to the moon still has the power to change the people who do it and the people who watch. On April 10th, 2026, the Orion spacecraft named Integrity splashed down in the Pacific Ocean off the coast of San Diego. The crew was recovered by the USS John P. Murtha. They underwent medical evaluations. They were flown to Johnson Space Center. They debriefed. They shared their data. And then they tried to describe what they had seen. They failed in the best possible way, not because they lacked the words, but because the experience exceeded any available vocabulary. Which is, as it turns out, exactly the right kind of failure. The experiences that matter most are always the ones that outlast the language we bring to them. Somewhere above us tonight, on the near side of the moon, lit by sunlight and visible with a good pair of binoculars at the right point in the lunar cycle, there is a bright spot near the Glushko crater. It sits at a specific latitude, just visible from Earth when the moon is positioned correctly. Its formal name is pending International Astronomical Union approval. Its name is Carol. Two girls in Maryland in Texas can look up on a clear night and find a feature on the surface of another world that carries their mother's name. They can point to it. They can show it to other people. They can say, "Our father went to the moon, and when he got there, the first thing he did was name something beautiful for her." Jim Lovell told the crew not to forget to enjoy the view. They didn't. And from here on Earth, looking up at the same moon that has hung above every human being who has ever lived, the same moon that lit ancient campfires, that pulled the tides, that gave us our sense of a month and our first calendar, we are lucky enough to be alive at the moment when people started going back. The moon is not asking us anything. It is just there, 238,900 miles away, patient as it has always been, turning the same familiar face toward us night after night, while the other face, ancient, battered, cold and strange, keeps its eternal vigil on the far side of the dark. But we went around, and we looked, and what we found there was not only science, and not only wonder, though it was both of those things. What we found there was ourselves. If you found this journey through the Artemis II mission valuable, please consider subscribing and leaving a comment below. We would like to know, what surprised you most about what the crew found on the far side? And what do you think we will discover when Artemis III finally lands? The moon has been waiting for us. It will keep waiting. But it is worth going back.